Hello. In the last video, I raced a river, but I didn't declare a winner, and that's because in order to do that, we need hard empirical data, which is why after I crossed the finish line, I spent about 2.5 hours throwing rope over a bridge railing to measure the river's water level and speed. And this is what that data looks like. You can see that I collected data every 15 to 20 minutes. Height is the distance from the bridge top to the water surface, not to be confused with water level. Water level is calculated by subtracting this number from 7 meters. 7 meters is the base flow height. Base flow height being the water level on a day that it didn't rain. If we take the water level and multiply it by 100, we get our area. 100 meters is the width of the channel under the bridge. Next, we look at speed, and speed is a little more difficult. Speed isn't measured speed. Speed is actually how many seconds it took for the rope to become fully taut, like this. Now, we calculate speed by using Pythagorean's theorem to find the distance traveled, and then divide that over the time recorded. If we take both of these equations and put them together, we get discharge, and discharge is our formula up here. Now, if we take this formula up here and input it into Excel, we can automate our calculations and visualize it with a graph. This is the graph. But before I show you, I want you to think clearly and meaningfully about this. Who do you think won the race? Was it me, or was it the river? Okay? You got your answer locked in your head? Written down on a piece of paper maybe? You're okay? Alright. The data says the winner of the race is me. Yeah, it's me. Of course it is. Of course it is going to be me. Let's look at the data. It says that I reached the finish line during the rising limb of a storm event, which means that I beat out the lag time. I was faster than the river could do its job. But I also want to make one thing clear here, and that is that this interpretation, this analysis, it's subjective. You, the viewer, are well within your right to interpret this data as you please. I'm not trying to make any definitive scientific claims by showing you this data. Rather, what I'm trying to do is I'm using the scientific method to persuade you that with the hypothesis that I proposed, the rules that I set, and the conditions that I met, that I won this race. I am the rightful winner. I am faster than the river. And if you accept these conditions, then there's really only one question left to ask, and that is, how did I know I would win?
Am I a wizard? Did I cheat? Was the water a paid actor? The answer is no. I made a calculated guess. I relied on all my knowledge of geography, and I trusted my intuition. I think a good way to develop a bit of this intuition would be to look at some famous examples of rivers around the world and see what their lag times are. Let's start with the famous Nile. The longest river in the world, spanning over 7,000 kilometers, has an impressive lag time of 2 to 3 months. What? Okay, but you have to remember, you're not just measuring the time of concentration, you're considering how the entire system of tributary rivers collects and converges water through a network of meandering paths. And when the watershed spans something near half the length of Africa, 2 to 3 months kind of makes sense. So then, let's lower the stakes. The longest river in Japan is the Shinano River, spanning a respectable 367 kilometers with a lag time of 6 to 12 hours. And this kind of makes sense. Smaller scale equals smaller lag time. Now, obviously, 7,000 to 300 is a big jump, but it gives us a frame of reference to what we might expect from a river even smaller than this. So with the Muromi River traveling a total of 15 kilometers, what do you think the lag time would be? Put a pin in that, because while it's fun to build this type of intuition based on simple pattern recognition, there is a more scientific way to estimate lag time. This is a paper published by the US Department of Agriculture, and it models lag time with a very simple equation. Now, I'm showing you this to highlight the importance that scale has in determining lag time. However, we already saw the effect of scale on lag time when we looked at the last two examples. So why am I showing you this? Well, I'm showing you this because this paper mentions several other factors that influence lag time, and each factor is closely related to one another. Let's start with slope. Slope is related to scale in the sense that large watersheds often originate in the mountains, tall mountains, like the ones that we see behind us. Now, with tall mountains and steep slopes, the water has a chance to run down and pick up speed and be fast. However, that's not representative of the watershed as a whole. Take, for example, this area that I'm standing in right now. This is part of the watershed, and you'll see that the slope is quite flat. So, the speed of this water is quite slow. Now, we have to consider this when we're thinking about the behavior of the watershed as a whole, particularly when we're thinking about the time of concentration. But remember that time of concentration isn't everything when considering lag time. A different and perhaps more useful metric might be to conceptualize how water converges from all corners of a watershed into the primary stream. If a watershed is efficiently connected with all the tributaries feeding into one main stream, we call this having a high density, and this plays on the idea of watershed shape. We like to think of rivers as long lines cutting through the landscape, when in reality, rivers have to conform to the obstacles that already exist in the topography, and every other detour and turn adds on to the lag time. There is one other factor that perhaps isn't so obvious, but en masse can play a significant role in influencing lag time, and that is this: surface conditions. Now, scientifically, this is labeled as retardants, but that word makes me uncomfortable, so we're not going to use that word. And really, all it's referring to is this: the trees, the grass, the foliage, the soil, anything that impedes water from the sky to becoming water on the ground is your surface conditions. And in general, more vegetation means higher lag time because water is being slowed down and absorbed into the river. And there are a couple of other factors that influence lag time, but these are the major ones, the big ones. So with that, let's take all of this into consideration. And by take into consideration, what I mean is let's piece together how the Muromi River might behave in terms of lag time. The leading variable here will be scale, which, as we saw before, was relatively small, so we can expect a decently fast lag time. Next, let's take a look at shape and slope, starting with slope. There are a lot of mountains in this area, so that must mean that there's a lot of steep slopes, right? Well, yes and no. While there are definitely some impressive mountains where the catchment begins, the position of the mountains and the shape of the river means that a lot of the momentum is lost having to meander around the mountain which it comes from. Then, by the time the river enters the city, you'll notice that it's mostly flat land from the valley to the sea. This aspect does not bide well with producing an efficient lag time. Lastly, while it doesn't play the largest role, surface conditions are still worth mentioning. Fukuoka likes to present itself as the city of flowers because of its generous flower beds and green arrangements, which you can certainly see spotted around the urban downtown. But in general, most of the surface conditions come from the far more traditional rice fields and their adjoined irrigation networks. I'd also be remiss if I didn't mention the equally traditional and impressive soko, or drainage networks, which bypass water through important infrastructure and feed it directly to the river for efficient discharge. And with that, all the cards are on the table. So it's finally time for us to check our answers. Are you ready? If you guessed 1 to 2 hours, you were spot on. And I had the same guess. And already knowing that I could race from the dam to the delta in less than an hour, you can begin to understand why I felt so confident taking on this challenge. But the magic for me in all of this is that my estimate lined up almost perfectly with the observed data, which is kind of the perfect ending to this exciting little experiment of mine.
This is the end of the river. Or rather, this is where the river ends. Out into Hakata Bay and then into the sea. This is also where this video series ends. And I don't like endings because it's hard to pick just one strong point to finish on. But if I had to choose, I'd say this. In conclusion, I had fun. And I hope that these videos were educational. I hope that they were entertaining. I hope that they were enjoyable. I hope a lot of things, but ultimately, the thing that I hope for the most is that at the end of this journey that you've come along with me on, that you take something away from this all. Maybe you learned something new. Maybe you found a new perspective to see the natural world around you. What I hope for the most, though, is that you gained an interest in something that you didn't realize was interesting. Because that's what this is all about. Not teaching science as a goal in and of itself, but rather using science as a vehicle for curiosity. When I started this project, I didn't do it because I like teaching. I mean, I love teaching, but that's not why I did this. I did this because I like rivers. I love rivers, in fact. And I had this silly, fun idea that just made sense to me. And honestly, whether or not I was able to win this race wasn't important, because just working through the process and spending time in nature was all the reward that I need. It's one of my many passions, and I wanted to share that passion with you, with the world. And so, for your part in that, thank you. But speaking of audience participation, I have to say this. Do not do this. Do not try this at home. I put myself in many of harm's ways. I could have been buried under a landslide. I could have been struck by lightning. I could have been swept away by the river. But I mean, still, the scariest thing for me is if the police pulled me aside and decided to question why I was throwing a rope over a bridge, because how do I explain myself? But enough stalling. I proposed the hypothesis. I made the tools. I collected the data. I ran the numbers. I raced the river and won. Thank you for watching. I'll see you in the next class. Until then, take care.